In today's demo, we'll be showing how DDN enables high-performance KV caching for AI inference workloads. As part of an AI pipeline, inference has a number of challenges that can make or break the effectiveness and economics of an AI solution. When using the latest models, context windows continue to get larger and larger. This has a direct impact on the amount of tokenization, and as we'll show later on in this demo, latency of time to first token and overall response time. And finally, scale matters. GPUs and CPUs typically only use localized memory to feed data into the GPU. Even if a shared memory structure is used, being able to retrieve a much larger set of shared context from a storage system pays dividends. The good news is that there is technology to help with this. Caching the tokens used for context can solve all three of those challenges. A bit of understanding first, though. When you enter a prompt, context is computed. If you continue a prompt chain, the model needs to see all prior prompts in order to understand the overall context. Without caching, it would have to recompute the prior context every single time. However, if the context tokens are cached, they can just be retrieved instead of being recomputed. This speeds up responsiveness in long prompt chains, lowers the latency of getting the tokens to the GPU after a prompt, and allows you to store much larger amounts of context that can be done in memory alone. It's critical to understand, though, that caching moves the ongoing work from the GPU to the cache storage system. In order to enable effective caching, the storage system needs to be able to provide both low latency and also large capacity at scale. As an example of capacity, we've calculated the needed KV memory needed for a variety of popular models such as Llama 2 7B, Mistral 7B, and Llama 3 70B. The larger the model used, the larger the KV memory needed. As the number of concurrent users go up, the memory requirements follow in a linear manner. Now, this is only for a single GPU. Picture an NVIDIA DGX system with 8 GPUs in it, and we can now see the possibility of needing terabytes of cache capacity for just a few hundred end users. This is where DDN helps. With our high-performance and high-capacity EXAScaler platform, we can make that cache work for you, allowing higher user concurrency, faster responsiveness, and a better user experience. So with that, let's demo. For this demo, we have an inference application. The configuration sends the same prompts to two different engines using the same model, Qwen3 32B. We've set the system prompt to be concise and the temperature is set to 0 so that the two engines will take fewer liberties and reduce variability between answers, making the comparison more accurate. We've also warmed up each model engine to prevent outlier anomalies during the first prompt request. The infrastructure behind this consists of two H100 GPUs and a DDN EXAScaler providing storage for the cached engine via GPU Direct Storage, otherwise known as GDS. We're going to upload a genomic sequencing white paper that has a relatively small context and consists of just under 6,000 tokens, and then we'll ask for a summarization of the article. Looking in the graphs on the left, because no context has been cached, the time to first token is very similar between the two engines. The total response time for the cache side is actually slightly longer due to the overhead of creating the cached tokens, computing attention, and then storing them. When we ask a further question, you can see the time to first token for the cached engine is now much faster than the uncached one. Again, however, at small context lengths, the total response time is almost the same due to the overhead that was previously mentioned. Now, let's add a much larger document and a new prompt to show the effect of more scale on tokens and compute overhead. With the new document and the additional context of a new prompt that references it, the input token size grows significantly. As a sidebar, when you add additional context and content, the computation overhead grows as the square of the context size. So for 10,000 token context size, it requires 100 million quadratic calculations. A 50,000 token context size becomes 2.5 billion calculations. As context grows, This means caching now has a distinct performance advantage over recomputing the context each time. As expected, because the prompt mostly referenced information in the new document, there was minimal existing caching, so cache had little impact on the overall performance. However, as we asked further questions that referenced the newly cached content, you see that with a larger context, caching has an even larger impact on the performance. In this case, showing 10x improvement, while before it was only 3x with the much smaller context. Takeaway for this is that in a dynamic scaled out environment where additional data and context continues to come in, there will be a significant compute overhead. But once the cache is built, there is a faster response moving forward, and the GPUs no longer need to calculate the tokens, freeing cycles for the GPU to handle other user requests. The final thing to look at is the capacity implications of KV caching. Even with a small number of input characters, approximately 200,000 between the two documents we uploaded, have resulted in the cache being populated with 796 files consisting of token chunks and metadata at a size of almost 13 gigabytes. If you're using KV caching to accelerate the end user experience, this puts a premium on having extremely high performance shared storage to serve those tokens. DDN has also performed extensive testing, and we've shown that depending on the model used and prompt length, EXAscaler performance can power KV caching to provide anywhere from 10 to 25x improvements in time to first token during inference. As we've shown in this demo, when context continues to grow along a chain of prompts or conversation, KV caching becomes more effective. As enterprise AI scales out, this means that DDN can make KV caching more effective by improving response times, more consistent by providing a larger cache repository space, and more cost-effective by delivering the combination of performance and capacity density to meet the needs of many concurrent users.